Hi everyone. In our last video, Romit spoke about audio tokenizers and explained how they are built. We are releasing a library. You can use it to tokenize your own audio. I have added the link in the description. It is really fast. It can process about an hour of audio in 1 second. We are also releasing a tutorial on how to build your TTS using these tokens. And please do not forget to start the repo. So today I'll cover the part 2 of this series. It is about building audio models using these tokens and also how TTS models are usually built. So as we discussed in the last talk, semantic tokens and acoustic tokens, there are two different types of audio tokens. One captures how something is read, another captures how it is spoken. Now we know that transformers are really good at modeling sequences and tokens are sequences. So what happens when we train a transformer using audio tokens? So if you train only using acoustic, this is what happens.
Chirun Iru, Isis, Numakases.
And this is what happens when you add semantic tokens to the mix.
It was the best of times. It was the worst of times.
So as you heard, semantic tokens are able to model some language and they are much closer to what we understand as language. Whereas acoustic tokens do understand audio correctly, but they cannot model words or higher level constructs. So clearly semantic tokens are closer to the language that we understand. Now to build a TTS model, we need to convert text to semantic and semantic to acoustic. We do this with two transformers cascaded one after the other. The first transformer converts text tokens to semantic tokens. This one figures out how something is read. For example, PUT is read as put and BUT is read as but. This is what first transformer does. The second figures out how P or ut or ut should be spoken. So this chain converts given text into semantic and then semantic to acoustic. Semantic tokens have a problem. They do not capture any voice characteristics such as gender or depth of voice, and every run of this structure will produce a different voice. So for example, here is the first run.
Twinkle, twinkle, little star, how I wonder what you are.
And here is the second run.
Twinkle, twinkle, little star, how I wonder what you are.
Every run creates a different voice. When we are building TTS systems, we require consistency of voice. We cannot have them generate different voice every time they are run. So what we do is we add an extra prompt of acoustic tokens that profiles a person's voice and append it to the context. So for example, here is a voice sample.
Twinkle, twinkle.
And here is the audio generated with that voice sample.
Twinkle, twinkle, little star, how I wonder what you are.
As you can see, the audio generated was following the voice profile that was created. But to train a TTS system like this, we need a large amount of parallel text and audio data, which is not available for a lot of Indian languages like Marathi, Telugu, Tamil, Malayalam, etc. Now, but a lot of unlabeled data is available. For example, all the videos uploaded on the internet and all the text available on the internet. They're not parallel to each other, but they are massive in amounts. So what we do is we pre-train a model on all this text data and semantic tokens of the audio data and then fine-tune it to build a good quality TTS. Doing it like this, you can actually build a good TTS model for even low resource languages with as less as 50 to 100 hours of data. So current LLMs such as Llama model the world using text. They capture a lot of information using all this unlabeled data that was available on the internet. Can we somehow take this information and apply it to audio? Now these LLM models, the first layer is usually an embedding layer which takes text tokens and outputs vectors. What we can do is we had these semantic tokens. We can add more to these embedding layers, initialize them randomly and continue to fine tune the model both with text and audio. But we want this model to understand text and audio in same space. So we need to create examples which force it to use audio as it would be using text. So for example, here, in this audio clip, how many times was the word LLM spoken? And then we give it an audio clip. In this example, the LLM has to learn how to read this audio and figure out the word LLM and then learn how to count it. Similarly for generation, saying Mary had a little lamb in opera voice and an audio example of it really happening. Here the model would have to learn how to produce opera voice and also how the rhythm of Mary had a little lamb goes. Now with this, we have a model that can take and produce semantic tokens. This model can still understand text, that is not gone. So what can we do with such a model which can take both text and audio and produce text and audio also? So one, ASR TTS models were always there. We can chain ASR, LM, TTS and take in audio and produce audio also. But there are a lot of problems with a pipeline like this. For example, there are many sounds that cannot be written as text. This cannot be written as text. This can also not be written as text. An LLM which hasn't really heard audio cannot understand these type of things. So end-to-end audio models can actually understand these sounds and also produce them. They can also understand emotions and other nuances in our voice, such as hurry, and then they can reply appropriately according to these sounds. This model still understands text, which means we can prompt it with things which involve both text and audio. For example, I can teach it how to sing Twinkle Twinkle just by prompting it. I do not have to retrain it or fine-tune it to teach it something specific. Similarly, I can teach it how to speak certain words. For example, my name, Apurva, is spoken as Apurva and not as Aparva. I can teach the model to do this just by prompting it correctly. Previously, we would have to fine-tune and train our own models to do this. Pretty soon, you'll be able to talk to LLMs as you would talk to your friend. And that's an exciting paradigm for conversational AI, whether for companies or for individual use. Follow us and star our repo for further updates on audio models.